All right. Hey everyone. Welcome back to our seventh lecture. So this week's topic is fundamentals of algebra, so mainly polynomials. So as usual, our handout is posted on our website. We'll review the content on the handout for a bit and then move into some competition problems. So our first topic is, well, what is a polynomial?
So a polynomial is basically a function with powers of variables and a coefficient. So for example, a polynomial could be 3x squared plus 6x plus 2. Anything where there's increasing powers of an exponent and next to each of them there's a coefficient is considered a polynomial. So one of the main things to consider for a polynomial are the roots of a polynomial. So many polynomials, the roots are the values of x for which the polynomial is equal to 0. So let's say we took the polynomial x squared minus 2x plus 1. This polynomial, if we plug in x equals 1, we get 1 minus 2 plus 1 equals 0, which means that x equals 1 is a root of this polynomial. So in other words, we can also write polynomials in terms of their roots. So for this polynomial specifically, x minus 1 is the only root, and we could write this polynomial as x minus 1 times x minus 1 equals 0. And this format is great for expressing understanding how the polynomial works better, as only when x is equal to one of the roots will the overall function be 0. So next we'll move into some of the topics that help us identify the roots. The first main thing is called Descartes Rule of Signs. So for a polynomial of degree n, so for example, degree n is the exponent of the largest power. So for example, for this thing, the degree of the polynomial is 2. But if we had some other polynomial where the largest power was x cubed, the degree would be 3. And any polynomial has n roots if the degree is n. But additionally, not all the roots of a polynomial are real. Some of them are imaginary, but imaginary numbers are their own topic, so we won't discuss them much for now. Descartes is useful for giving us a better idea of how the real roots work, specifically how many positive and negative roots are used. And to use it, we look at the number of sign changes in the coefficients of the function. So for example, if we took something like 6x to the fourth minus 3x squared cubed plus 6x squared plus 4x minus 2 or something, right? To use Descartes' rule of signs, we look at specifically the coefficients, which are plus 6, minus 3, plus 6, plus 4, and minus 2. And we look at the points where this sign changes. So the sign changes once in between here, once in between here, and once in between here, for a total of 3 sign changes. So what Descartes' rules of signs tells us is that since there are 3 sign changes, there are either 3 or 1 positive real roots. Similarly, for negative roots, we look at the function f of negative x instead. That just means that for every x, we replace it with negative x. So the function becomes 6 times negative x to the fourth times 3 times negative x cubed plus 6 times negative x squared plus 4 times negative x minus 2, which if we simplify just becomes 6x to the fourth plus 3x cubed plus 6x squared minus 4x minus 2. And now once again, if we look for the sign changes, we see that they only occur once, which means there must be 1 negative real root. So Descartes' rule of sign isn't that useful on its own, since it just tells us the number of roots. So there are more complicated, there are more useful things to further narrow down the roots. One of them is called the Rational Roots Theorem. And it's much more useful since it gives us an idea of what exactly the roots might be of a polynomial. So if we have some random polynomial of the form a0 times x to the n plus a sub 1 times x to the n minus 1, and so on all the way up to a sub n, we can basically see that all of the rational roots, which means that it can be expressed in the form m over n, where m and n are integers, have to have m as a factor of a sub n, and n is a factor of a sub 0. So this is very useful as it lets us heavily narrow down which roots to test when trying to factor polynomials that don't follow the factoring rules that we'll mention later in this lecture. So next we'll move on to synthetic division, which is a way to actually test out whether a number is a root of a polynomial. It's basically a way of dividing a polynomial by a linear factor, and we'll go through a couple of examples to show how it works. Let's say we want to divide the function x cubed minus 2 plus 2x squared minus 7x minus 2 by x minus 2. In other words, we're basically checking if 2 is a root. So to do this problem, we have to set up basically a synthetic division. To set up synthetic division, we create this inverse division thing almost, and we listed the coefficients over here, 1, 2, -7, and -2. And as we're testing if 2 is one of the roots, we'll place 2 over here. Now to do synthetic division, we start by moving the 1 down, then we multiply it by the root and move it up to the next thing, which would give us 2. Next, we would add these 2 to get 4 down here, and then again multiply by 2 up here to get 8. We'd add again to get 1, multiply by 2 to move up here to get 2, and then finally, when we add again, we get 0. So if we want to express this algebraically, this simply means that this term is equal to x squared plus 4x plus 1, with a remainder of 0. So this is basically a quick way to test roots, since if the remainder is 0, it basically tells us that it's the x minus 2 is a root of this function, and we can write that x cubed plus 2x squared minus 7x minus 2 equals x minus 2 times x squared plus 4x plus 1. But synthetic division is basically only works when you're dividing a polynomial by a linear root, which means like x plus a or x minus a. And in those cases, it's really quick for testing for roots. Finally, the other topic is a remainder. There are circumstances where this number will not be 0, and that just means that it's not divisible by that factor. So if we are looking for the remainder of a function f of x divided by x minus a, the remainder of that function is always equal to f of a. So if it's a root, f of a would be 0, which means that it's perfectly divisible. But if a is not a root of the function, then we'd have some remainder. So more formally, we'd get that f of x equals some function g of x times x minus a plus the remainder f of a. Now we'll go over some of the more common factorizations, which would save us from having to do the rational roots theorem and synthetic division every time to find the roots of a polynomial.
All right, so one type of factoring, so some of the very common types of factoring are, first of all, difference of squares. So what difference of squares is, we've mentioned it in earlier lectures. So anything in the form of, let's say, x squared minus y squared can be factored into the two terms x minus y and x plus y. So if you expand this out, we would get x squared minus xy plus xy plus y minus y squared. And you can see the middle two terms cancel out, so we get the difference of squares. So this difference of squares comes up a lot in competition math, in algebra as well as occasionally number theory. So it's very useful. Moving on, we also have difference of cubes. So let's say we had x cubed minus y cubed. This again can be factored into x minus y times x squared plus xy plus y squared. And in general, for any x to the n minus y to the n, it can be factored into x minus y times x to the n minus 1 times x to the n minus 2 y time plus dot 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 all the way down until y to the n minus 1. So moving on, we have a very famous type of factoring, colloquially known as Simon's favorite factoring trick. This is very popular on AOPS by Richard Rusrick in his Math Counts mini videos. So what it is any expression in the form of xy plus a plus b plus ab can be factored into x plus a times, or x plus b times y plus a. So this is very useful when dealing with multiple variables, especially if those variables are integers. So like if you're trying to find the dimensions of a box given some sort of restriction. So we'll go over some more of these problems later on. So the next major topic with polynomials, probably arguably the most important topic on polynomials is Vietas. So some of you guys may have heard about this, but if you haven't, basically it's if you expand out the root form of a polynomial, so like x minus r1 times x minus r2 times dot 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 times x minus rn, the coefficients are just like they cycle between signs. So if you look at the polynomial uh, a sub 0 of x to n plus a sub 1 x to the n minus 1 dot 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 all the way to a sub n, well, the coefficient a sub 1 would be negative of the sum of the roots. Because if you expanded it out, every term with um, x to the n minus 1 would just be like if you looked at our root form, if you expanded it out, it would just be negative r1 times x to the n minus 1 plus negative r2 dot dot dot. So we get that as negative of the sum of all the roots. And we can continue this with all the other forms. So you say if you look at a sub 2, it would be equal to the sum of the pairwise product. So a sub 1 times a sub 2, or not, or r sub 1 times r sub 2 plus r sub 1 times r sub 3 plus dot dot dot, then plus r sub 2, r sub 3, r sub 2, r sub 4 dot dot, all the way until r sub n minus 1 to r sub n. So and this continues down. So for a sub 3, it'd be not instead of pairwise, it'd be pairs or triples of roots, like so, and then so on. So if you look at this for quadratic, if you had, let's say, the quadratic x squared plus, or let's say you had the instead of it being monotonic, let's say it was ax squared plus bx plus c. Well, we can actually rewrite this as a times x minus r1 times x minus r2, since the leading coefficient is a, right? So if we were to expand out our our root form, we would get ax squared plus a times negative r, so negative a times r1 plus r2 x plus a r1 r2. So what we get is the product of the two roots r1 r2 equals c over a, and that the sum of the roots r1 plus r2 would be negative b over a. And this applies to all quadratics. So if you were to do this with cubics, etc., the forms of the equations would be a bit different, but in general they'd be similar, where they alternate signs based on the degree, and you have like products and sums of products, etc. So these are extremely useful and they often come up a lot. So right now we'll just get into some competition problems that involve these various topics.
All right, so our first problem is we want to find the average value of the three roots of this equation, x cubed plus 12x squared plus 4x plus 48. So right away, we can notice that we can try to factor this, since we see the 1 and 12 and then 4 and 48 for consecutive powers of x, which means that x plus 12 is probably a root. So we can rewrite this as x plus 12 times x squared plus x plus 12 times 4. And this would basically give us that we get x squared plus 4 times x plus 12. Now wait, we can't exactly factor x squared plus 4 anymore since we get imaginary roots, since all squares of real numbers are positive. But actually, imaginary roots don't really change anything when we take the average. The roots would actually be plus or minus square root of negative 4, which if you add them up, just sum to 0. So if we add in the negative 12 from earlier, from this factor, the sum of the roots is simply 0 plus 12, 0 plus negative 12, which is negative 12. So the average is negative 12 over 3 equals negative 4. But that took quite a bit of work, and we had to deal with imaginary numbers, which are really hard to deal with sometimes. Since all we wanted was the average for this problem, we only need the sum of the roots. And we can actually use Vieta's formulas to find this. Through Vieta's, we know that the sum of the roots is the negative value of the second coefficient, which is 12. So we already know that R1 plus R2 plus R3 equals negative 12 just from Vieta's formula. So the average is simply just negative 12 divided by 3 equals negative 4, as we got earlier. So this is just meant to demonstrate how Vieta's is really useful whenever you're dealing with sums or products of roots. So now we'll move on to our next question. So we have two numbers a and b that are non-zero and real, and we have that the equation x squared plus ax plus b equals 0 has the solutions a and b. And we want to find out what the pair a comma b is. So over here, we have the roots of the polynomial are the same as the coefficients of the second and last term. Since the roots are a and b, using Vieta's, we can get that a plus b has to equal negative a, and that ab equals b. So right away, the second equation instantly tells us that a has to equal 1, since a and b are non-zero. And then using the first equation, we get that 1 plus b equals negative 1. This means that b has to equal negative 2. So the only option is that b is negative 2 and a is 1. So therefore, a polynomial is simply just x squared plus x minus 2, which can be factored as x minus 1 times x plus 2, which gives the roots are 1 and negative 2 as we got for a and b. So on to our next question. This is another Vieta's one. So we have a fourth degree polynomial this time with x to the fourth minus 7x cubed plus 4x squared plus 7x minus 4. And we're given that all four of its roots are real, and we want to find the sum of their reciprocals. All right, so instead of dealing with the sum or product here, we want the sum of the reciprocals. And even worse, this is a fourth degree polynomial, so we don't exactly know how to deal with it right off the bat. But since we're dealing with the reciprocals of the root, we obviously can't use Vieta's right away. Or can we? If you remember from Vieta's, we get that ABCD, if those are the four roots, would equal 4. Equal negative 4, sorry. And also that ABC plus BCD plus ACD plus ABD, which are the sums and triples, would equal negative 7. Now, if we take this, the first equation, and divide by the second, if we take the second equation and divide by the first, we'd get that ABC, and divide this by ABCD equals negative 4. We basically get that each of these terms cancels out with the denominator for all of the terms except for 1. And this just becomes that 1 over A plus 1 over B plus 1 over C plus 1 over D equals 7 over 4. So this basically shows how you can use the different equations from Vieta's for each of the coefficients and combine them in different ways to get sums that aren't just stereotypical, like A plus B plus C plus D, or the products. Next, we'll move on to a slightly different question about remainders. So we want to find the remainder when this function 5x plus 9 raised to the 611th power plus x plus 5 raised to the 11th power plus x minus 1 raised to the 11th power plus 3x squared plus 1 is divided by x plus 2. So obviously it's impossible to factor by hand since the coefficients, the degree is much too large. So we can use what's called the division algorithm. The remainder, as we talked about in the beginning, the remainder of a polynomial when divided by a linear factor, such as x plus 2, is just plugging in the solution to plugging in that factor to the polynomial. In this case, the solution for x plus 2 is just x equals negative 2. So the remainder would just be f of negative 2 equals r. Plugging it back into our original equation, we get that 5 times negative 2 plus 9 is just negative 1 raised to 611 plus negative 2 plus 5, which gives us 3 raised to 11, plus negative 3 raised to 22, plus 12 plus 1. And this thing, there was a mistake with this problem, but it should have been raised to the 1 and raised to the 1 here. So this thing simply would have given us that if these two terms would cancel out, this term is simply -1. And then the final term is just 12 plus 1, which means our overall expression would just equal 12. All right, now moving on to the next question. Here we have to use a more specific version of the division algorithm, which is the factor theorem. Since we are dividing by a non-binomial divisor, we can't use the division algorithm. And so since x squared plus x plus 1 divides our polynomial, the roots of x squared plus x plus 1 must also be the same roots of this polynomial. We can't really factor x squared plus x plus 1 since it gives imaginary roots, but why don't we just call the root, let's say, omega? That just means that we have omega squared plus omega plus 1 equals 0. So now, in this case, we notice that this looks somewhat familiar to the difference of cubes factoring that we mentioned earlier in this lecture. Specifically, we can multiply both sides by omega minus 1. And this gives us that omega cubed minus 1 equals 0. So obviously, we know that if we plug in omega into the polynomial, we get that omega raised to the 101 plus a omega plus b equals 0. And omega raised to the 101 is just equal to omega raised to the 3 raised to the 33 times omega squared, which is equal to, since we know that omega cubed is equal to 1, based on this thing, this is just equal to omega squared. So therefore, all we get that this equation is just omega squared plus a times omega plus b equals 0. And since we already know that omega is the solution to x squared plus x plus 1, that means that a and b must be, this basically is the same equation as this equation. So a and b must both equal 1.
All right, so our next question, we have the harmonic mean of, oh, wait. Sorry, wrong question. So we have the q roots of ax cubed plus a plus 2bx squared plus b minus 3ax plus 8 minus a equals 0 are -2 and 3. And we want to find the third root. So we've already gone over a bit about Vietas and the division algorithm so far. So this question kind of mends both of them together in one problem. So here we go. So we're already given two of the roots. So right off the bat, we know we can use the factor theorem. So when we plug in -2 and 3, the polynomial reduces down to a plus 6b plus 8 equals 0, and 26a plus 21b plus 8 equals 0. So this gives us a system of equations for which we can solve if you multiply the first, it's 26 plus 21b plus 8, not 1, my bad. We can rewrite them as a plus 6b equals -8 and 26a plus 21b equals -8. Equals -8. Yeah, so well, if you take the first equation, we can multiply by 7/2, and we would get 7/2 a plus 21b equals -28. So if we subtract this from the second equation, we would get, well, 26a is 52/2 a, so minus 7/2 a would just be 45/2 a. The b's cancel out, and we would get this is equal to 20. So solving for a, we get that a is equal to 8/9. So when we plug this back into our original equation, we get 8/9 plus 6b equals 8. So that 6b equals negative 80 over 9. So b equals 40 over 27, or negative 40 over 27. So we solved for both a and b. So what we could do right now is we could plug all these values back in, and we would get our cubic polynomial, and then we would factor it since we know two of the roots. But that would be a lot of work, especially since these numbers are very, well, not integers. So what we can do is actually we can use Vietas to make things easier. Since we know that the sum of the roots is equal to negative a minus 2b, which is the coefficient of the second term, we would get that our root, let's say our root is called r, we would have r minus 2 plus 3 is equal to negative a minus 2b. So plugging in a and b, we would get that r plus 1 is equal to 56 over 27. So solving for r, we would get that r equals 29 over 27. So here, our problem kind of used both of our topics we mentioned, and in general, just made the problem much easier. Instead of having to, like when we use Vietas, instead of plugging everything in, we can just, well, plug it in for one term, and solving for the roots allowed us to solve for everything in the polynomial. So yeah. So moving on, a next genre of questions, I guess this consists of multivariable like expressions. So these are what we call Diophantine equations, which are equations that involve more than one variable. And generally we only consider them over integers. Like in this case, we have two positive integers. So it asks us the harmonic mean of two positive integers, which is the reciprocal of the arithmetic mean of the reciprocals. So it'd be 1 over x over 2, or 1 over x plus 1 over y over 2. So you could just put the 2 in the numerator. So this just becomes 2 over 1 over x plus 1 over y, which further simplifies if you clear the denominator into xy, or 2xy over x plus y. And it wanted us to find all of xy such that this equals 20. So this seems pretty messy right now. So I guess the first thing we could do is just clear the denominator. That's never a bad approach since denominators make things messy usually. So we have, this becomes 2xy equals 20x plus 20y. Well, we can already see this somewhat looks like our Simon's favorite factoring trick. So why don't we try moving everything to one side? We get 2xy plus 20x plus 20y equals 0. Well, we can divide both sides by 2 now, so we would get xy minus 10x minus 10y equals 0. And this looks a lot like x minus 10 times y minus 10. So we can actually write as x minus 10 times y minus 10 minus 100. So moving the 100 to the other side, this equals 0. We would get x minus 10, y minus 10 equals 100. Well, since we know that x and y are positive integers, x minus 10 and y minus 10 are both at least or strictly greater than negative 10. So that means, well, both of these are integers. So each term, x minus 10 and y minus 10, have to be a factor of 100. So we can either have both of them are positive or negative. But we can see if both of them are negative, but both of them are strictly greater than negative 10, their product would have to be less than 100. So both of them have to be positive, since if they're negative, there is no solution. So that means if both of the terms are positive, since there are no other restrictions, we basically get that x minus 10 is some factor of 100 and y minus 10 is the corresponding pair. So we just want to find the number of pairs of factors. Well, this is just the same as the number of factors of 100 because regardless of which pair x minus 10 is, there's always another value of y minus 10 that makes it multiplied to 100. So we want to find the number of factors of 100. So if we go back to our lesson from last week, we know that the number of factors is just 1 plus each of the powers. So 100 can be written as 2 squared times 5 squared. So there's 2 and 2. So this becomes 2 plus 1 times 2 plus 1, which is 9. So that means there are a total of 9 ordered pairs. So here again, we have another problem where there are multiple variables. We have P and T. So a mathematician works for T hours per day and solves P math problems per hour, where T and P are positive integers. And 1 is less than P is less than 20. So one day, the mathematician drinks some coffee and discovers he can now solve 3P plus 7 problems per hour. In fact, he only has to work for T minus 4 hours that day, but he still solves twice as many problems as he would in a normal day. So how many problems did he solve the day he drinks coffee? So, well, we can see we have this equation where on the day he drinks coffee, he solves 3P plus 7 problems times T minus 4 hours. And we know that this is equal to twice what he does on a normal day, which is just PT. So this is equal to 2PT. So if we expand this out, we get 3PT plus 7T minus 12P minus 28 equals 2PT. If we move the 2PT to the other side, we get PT minus plus 7T minus 12P equals 28. So we can factor this now. So we get P plus 7 times T minus 12 plus 84 equals 28. So then we get P plus 7 times T minus 12 is equal to negative 56. So obviously there are many solutions to this, but if you go back to our problem, they have to give us a restriction. P is greater than 1 and is also less than 20. So what this also says is that, well, 8 is less than P plus 7, which is less than 27. So that means we want to find a factor of 56 that is between 8 and 27. And the only factor is actually 14. So we know that P plus 7 equals 14, and thus T minus 12 is equal to negative 4. Solving for P and T, we get P equals 7 and T equals 8. So we want to evaluate how much he solves on a day he drinks coffee, which is just 2 times P times T. So P times T is 56, so 2 times P times T would be 112. And that is our final answer. So now, this is like, I guess, the last major type of polynomial problem, which involves discriminants of quadratic expressions. So we have this quadratic with a leading coefficient of P, which is non-zero, such that Px squared minus 12x plus 4 has exactly one solution. So, well, we know that a quadratic has one solution if and only if the discriminant is equal to 0. So that means, well, the discriminant would have to be 0. So we have b squared minus 4ac has to be equal to 0. So plugging in values, we get that b squared is 144, since negative 12 squared is 144. And we get that minus 4ac becomes minus 4 times 4 times p. And that equals 0. So what we get is 144 minus 16p equals 0. And we get p equals 144 over 16, which is equal to 9. And that is our solution, p equals 9. All right, so I guess
Also, as a quick additional note, the reason that we look at the discriminant is because if you remember from the quadratic formula, the roots of a polynomial of a quadratic are just minus b plus or minus square root of b squared minus 4ac all over 2a. But if this term, the b squared minus 4ac, is 0, both the roots happen to be the exact same thing. So there's only one solution. So as Adam did in this problem, we simply want to set this inside to equal 0.
All right, so we'll be moving on to, I guess, a few harder problems. So here we have the graph of y equals x to the 6th times x to the 6th minus 10x to the 5th plus 29x to the 4th minus 4x cubed plus ax squared lies above or strictly above the line y equals bx plus c. And except for at 3 values of x where the graph and the line intersect or touch. So all we know what this should look like is that the entirety of the function lies above the line, except for at 3 points where they touch and then go back. So, well, if we draw this out, it would kind of look like a 3-humped W that touches a line 3 times. Like so. So at each of those bases, we would have it touch once. So, well, this seems pretty confusing at first, or seems very difficult, because what we have is, well, we're involving the graphs of 2 different polynomials. So how exactly will we do this? Well, one way we can actually make this a lot easier is, instead of considering 2 polynomials, why don't we just take the first polynomial and subtract the second polynomial from it? Then we would just get everything shifted in a way such that we'd still have a 6th-degree polynomial, except instead of finding where it touches the line, we'd be finding where it touches the x-axis. And that's because the 2 graphs touch when the difference between the functions are 0. So if we take the difference between the functions and find their zeros, that is the same x-coordinate as what we're trying to find. So what this becomes is x to the 6th minus 10x to the 5th plus 24x to the 4th minus 4x cubed plus ax minus bx minus c. And we want to find the zeros for this. Well, what else do we know about this polynomial? Well, we know that whenever it touches the graph, so whenever our new polynomial touches the x-axis, it returns and goes up. So what this signifies is that at each of the zeros is actually a double root, meaning it's in the form of x minus r1 squared times x minus r2 squared times x minus r3 squared. And this is just a property of function. So when it double touches, it's a root of degree of an even degree. So since it touches at 3 places and of a 6th degree, each of them has to be of degree 2. So what this tells us is that our polynomial is actually in the form of x minus r times x minus r2 times x minus r3, and all of that is squared. Squared, right? So let's rewrite the inside as just like a normal cubic function, like let's say x cubed plus mx squared plus nx plus k. You get that this function squared is equal to the polynomial from above. So if we were to expand this and we were to look at each term, well, obviously x to the 6th is equal to x to the 6th. But if we looked at x to the 5th term, we would get that the x to the 5th term in our expansion would be, well, mx squared times x cubed plus mx cubed times mx squared. So it'd be 2mx to the 5th. And this equals negative 10 to the 5th. So that means we get that 2m equals negative 10, so m equals negative 5. So if we continue this, if we look at the x to the 4th term, well, we know that the x to the 4th term is equal to 29. And this should be equal to, well, how can we make x to the 4th from our cubic polynomial? Well, we can have nx times x cubed times 2, because you can do it twice pairwise, and then mx squared times mx squared, and you can only do that once. So this is equal to, so we get that 29 is equal to 2n plus m squared. So since we already know that m is negative 5, m squared is 25. So we get a 2n plus 25 equals 29. So 2n equals 4, so n equals 2. So now all that's left is us to find k. So well, we can look at the x cubed term now. So the x cubed term would just be, well, 2 times kx cubed plus 2 times mn x cubed. And this should be equal to 4 or negative 4x cubed. So we get that 2k plus 2mn equals negative 4. So if we plug in our values, we get that 2mn is negative 20, which means that 2k equals 16, so k equals 8. So instead of having to find the rest of the terms in the 6-degree polynomial and factoring the 6-degree polynomial, we actually just want to find the largest root. And since we know that it's equal to our cubic squared, it shares the same exact roots as the cube. So that means we just want to find the largest root of the cubic. So we have the cubic polynomial x cubed minus 5x squared plus 2x plus 8 equals 0. And we don't want to find the largest roots. So how do you factor this? Well, cubics are a bit hard to factor, but we can just use the rational roots theorem in this case. So we can see the rational roots are plus or minus 1, 2, 4, and 8. So we can test 1 and we get 1 minus 5 plus 2 plus 8. That doesn't really work. But if we test negative 1, we see that we get negative 1 minus 5 minus 2 plus 8, which is equal to 0. So we can see that negative 1 is a 0. So that means this is factorable by x plus 1. So we factor it by x plus 1. What we get is x plus 1 so this over x plus 1 would be x squared minus 6x plus 8. And this one we can factor because we can see that x squared minus 6x plus 8 is just x plus, or x minus 4 times x minus 2. So we get that our polynomial is just equal to, or our polynomial has the roots negative 1, 4, and 2. So since these are all the roots, the largest one is 4. So our answer would be 4. All right, so here we have a more difficult aiming question. So let f of x be a third-degree polynomial with real coefficients satisfying the absolute values of f of 1, f of 2, f of 3, f of 5, f of 6, and f of 7 are equal to 12, and it asks us to find the absolute value of f of 0. Well, this doesn't really give us much to go off, I guess. We know the absolute values, but we don't know whether they're 12 or negative 12 or not. But actually, if we drew a cubic function, right, we can see that for any given f of x, which would be like a y level, it can be at most, there can be at most 3 different values of x, such that f of x equals this value. So that means since there are at most 3, that means 3 of f of 1, f of 2, all the way to f of 7, 3 of them are 12 and 3 of them are negative 12. And one more, here we drew a cubic polynomial with a positive leading coefficient, and we can see that the first value it passes through, if we start from the left, it would go through negative 12, it would go up until 12, come back down to 12 again, then to negative 12, and then go on to the hump again, negative 12, and then 12. So this is the case for a positive leading coefficient. If we have a negative leading coefficient, it would just be reflected, and then f of 0 would be just negative of what it would be for a positive leading coefficient. So since we're taking the absolute value, we can just assume that this is a positive cubic function. So here we have, so f of 1 equals negative 12, f of 5 equals negative 12, and f of 6 equals negative 12 based on what we can see on the graph. So we can see that all of these equal negative 12. Well, this doesn't really help us, does it? It's not like these are zeros. Or are they? Because actually, if we consider the function, let's say g of x equals f of x plus 12, we get that g of 1, 5, and 6 are all equal to 0 because, well, because f of 1, 5, and 6 are equal to negative 12, so g of 1, 5, and 6 is 0. So that means g of x has 3 roots. We know that g of x is also cubic, and it has roots at 1, 5, and 6. So g of x equals x minus, or kx minus 1 times x minus 5 times x minus 6. And we need the k there because we don't know how the function is scaled. The leading coefficient could be like 500 or 2 or something, right? And we get that this is equal to f of x plus 12. So that means f of x equals kx minus 1, x minus 5, x minus 6, minus 12. Well, now to solve for k, what we can do is just, well, we know that, let's say f of 2 is 12. We can just plug in q. So f of 2 would be k times 2 minus 1, which is 1. Then negative 3, then negative 4. Minus 12. So we know that 12k minus 12 is equal to 12. So 12k is 24. K is equal to 2. So now we just want to find the absolute value of f of 0. So we can just plug in 0. So we know that k is 2. So we get f of 0 equals 2 times negative 1 times negative 5 times negative 6 minus 12 equals, well, this would be negative 60 minus 12. So this would be negative 72. But remember, we're finding the absolute value of f of 0. So this would have to be 72. So this problem really showcases just like some crafty manipulations that you can do. And it also like shows like the helpfulness of actually drawing out the function and how it can yield very like useful observations, such as that f of 1, f of 5, and f of 6 have to be negative 12 while the rest are 12. So I guess moving on to our 12th question. For certain numbers a, b, and c, the polynomial g of x equals x cubed plus ax squared plus x plus 10 has 3 distinct roots. And each root of g of x is also a root of the polynomial x to the 4th plus x cubed plus bx plus 100x plus c. I guess for this problem, we want to find f of 1. I think it got cut off. So, well, to find f of 1, we just want to find all the coefficients. So we are given a very few coefficients. We're giving, in g of x, we're given the x cubed coefficient, the x coefficient, and the constant. While in f of x, we're given the x fourth coefficient, x cubed coefficient, and the x coefficient. Well, in general, the leading coefficients aren't very useful. Like if you remember from Vieta's, there was no useful information given from the leading coefficient if it was 1. So I guess the only ones that really matter are the 100x, the x cubed, the x, and the 10. So those are the important ones. So let's see what we can do with them. So let's look at the x cubed first. Well, so let's call the 4 roots of f of x r1, r2, r3, and r4. And let's say the 3 roots of g of x are r1, r2, and r3. So what this means is g of x times x minus r4 would be equal to f of x. So we have this. So if you look at the x cubed term in f of x, that should just be equal to negative of the sum of the 4 terms. So that means r1 plus r2 plus r3 should be equal to negative 1. This would be the sum of all 4 terms, or for all 4 roots. So this is equal to negative 1. Now let's see how we can use the other 3 coefficients that we know. Well, if we look how we wrote g of x times x minus r4 equal to f of x. Well, how can we relate the 100x to the x plus 10? Well, we see that we can see that 100x should be equal to the sum of the x terms of g of x times x minus r4. So 100x would be equal to, well, we have 10 times x, and then negative r4 times x. So minus r4 times x. So these terms should be equal. So that means you get that 10 minus r4 equals 100. So r4 equals negative 90. Now, since we know that r4 equals negative 90, and we know that the sum of all four roots is negative 1, that means the sum of the first three roots, r1 plus r2 plus r3, should be negative 1 minus r4. So the sum should be 89. And using Vietas, we know that the sum of these should be equal to negative a. So that means a should be negative 89. So we've basically solved for our entire polynomial g of x. We know that g of x equals x cubed plus minus 89x squared plus x plus 10. And so to find f of 1, we can actually just find g of 1 times 1 minus r4. Because we know f of x equals g of x times x minus r4. F of 1 equals, so then it would follow that f of 1 equals g of 1 times 1 minus r4. So we know g of 1 would just be 1 cubed minus 89 times 1 plus 11 plus 10. So that would just be 1 minus 89 plus 1 plus 11. And we know that r4 is negative 90, so we know that 1 minus r4 would be 91. So this becomes negative 77 times 91. And if you multiply this out, this is actually equal to negative 7,007, which would be our answer. So you can see how this problem is very reliant and heavily uses Vietas multiple occasions. And as you progress through like harder maths, problems including polynomials tend to become like this. It's not like a very obvious application of Vietas. It's more of like you go through many different layers and you have to figure out when to use it and when to not. So I guess here we're going to go on to our very last problem. So we have the polynomial f of x is such that f of x is equal to 6 plus f of x for all real numbers x. And we have f of x is greater than 0 for all x is greater than or equal to 0. Find f of x. So this delves into a more advanced topic called functional equations. If you want to learn more about that, you can probably find some resources online. I'd highly recommend AOPS. But we're not going to delve into that very deeply. We'll just go over some very basics. So we know that f of x is a polynomial. So this is very important because if f of x wasn't polynomial, this would be much more difficult because there could be any sort of function that satisfies this that's not a polynomial. So we know it's a polynomial. So let's say it's a polynomial of degree n. So like we talked about earlier, n is, when we say it's a degree n, it means that the largest power of x is x to the n. So since f of x has degree n, if we take f of x, that means the largest power would be n squared because f of x has a degree n, so you're taking f of x to the n something, so that would be x to the n, which is x to the n squared. So it has a degree of n squared. So since we know both sides are equal and they're all polynomials, that means both sides have to have the same degree because otherwise they would not be equal. So we get that the degree on the first side, so f of x is n squared. And this is equal to the max of either 1, since 6x has a degree 1, and the degree of f of x, which is n. So we can see if we have if n is less than 1, well, we would get that n is 0, and that obviously doesn't work. And otherwise, we would have, if we take max of 1 and n is equal to n, we get n squared equals n, so that means n equals 1. So that means the largest degree of this polynomial has to be 1. So that's a very important thing, because that limits down our search for polynomials from all of these different of various degrees to just to the first power. So this is something that's very useful with polynomials, is that if you have some sort of like equation between functions of a polynomial, equating their degrees is very useful because it often limits down the searches. This topic generally does not come up in math counts. It starts to show up more later on in, I guess, like harder AMCs, as well as, I guess, easier Olympiad questions. So this is definitely a very advanced topic. So if we consider that the degree of the polynomial now is first degree, we can write f of x in the form of, let's say, mx plus b, since we know it's first degree. So that means f of x would be m times mx plus b, and this would be m squared x plus mb plus b. So we get m squared x plus mb plus b equals 6x plus mx plus b. Since we have a 6, it's equal to 6x plus f of x. So, well, we can look at the constant terms first to get mb plus b equals b. So that means either m is equal to 0 or b is equal to 0. So we don't quite know which one yet. So let's look at the other term. We know that the coefficient of the x term is m squared, and this is also equal to 6 plus m. So this obviously implies that m can't be 0. So that means b has to be 0. So we know that b is 0 now. So let's solve for m. We get m squared equals 6 plus m. This becomes m squared minus m minus 6, which factors into m minus 3 and m plus 2, which gives us 2 roots, 3 and negative 2. Well, if there are 2 polynomials, why does it only ask us to find 1? Well, actually, if you look at the rest of the problem, it actually states that for f of x is greater than or equal to 0 for all x is greater than 0. So if f of x was equal to negative 2x, when x is greater than 0, f of x would be less than 0. So we can't, so negative 2 is actually extraneous. So that is not a solution. So that means m equals 3 is our only solution, which means that our function is f of x equals 3x.